Okay, good morning, everybody. Um, so I thought I would start by mentioning a common mistake on the last homework, which I probably should have mentioned last time. Um, but this has to do with using completeness in a correct way. So, uh, using completeness. So first of all, in order to use completeness, we have to have an orthobasis. And so I'm going to call that, for simplicity, a set of states J. And then if you do have such an orthobasis, then you can sum over J of ket J bra J. And that's an operator, which is equal to the identity operator. So let's consider one possible thing we could do with this, which is to use it for computing a matrix element between two states chi and psi of an operator A. So let's say we were going to compute something like that. So what a lot of people did on the homework, and there were several variations of this mistake, but a common thing to do was to write the following. So you write sum over J, chi, J, J, A, and then another J, J, and psi. Okay, and so the problem with this is that this is wrong. And so let's see how to do it correctly. So the correct way to do it is to not skip a step and put my chi here, and then I'm going to put a sum over J. Oops, that was wrong. JJ. And then my operator A. And then I'm going to put another sum, but I'm going to call this K. That's just a label, and I'm summing over that whole label, so it doesn't really matter what I call it. But the key thing is I can't call it J, because that's already used up in the first sum. Okay, so this quantity by completeness is equal to the identity operator. And this is also equal to the identity operator, but it's very important that the two labels that I'm summing over have to be independent. Okay, and so now I can write this as sum over J, sum over K, chi JJ, A, K, K, psi. Okay, and so that's the correct version. Okay, and it's important to notice again, the difference is that in the incorrect version here, I've mixed up the labels on my two identity operators that I've put in there. It's okay to put in the identity operator twice, but I have to be careful to label the things that I'm summing over independently. Okay, any questions on that? So people made several different versions of the same sort of mistake, but that's the idea. Okay.
I had a question about that.
Yeah, sure.
So, I believe that problem on the last homework was like trying to it was talking about the trace of like an operator, and that like that in the it had like the sum over like J of um J bra A J ket, and so how would you use completeness to get to a new I guess a new trace with a different orthobasis?
So if I understand your question correctly, it's really just a matter of doing an independent sum over an independent basis. So here we've assumed that we have some orthobasis, but this is supposed to be true here for any orthobasis, right? So I could
Yeah.
do a sum over j's, or I could do a sum over k's, where the k's might be the same list as the j's, but they might be a different list as long as each list is an orthobasis, it's okay. So we've seen
Okay.
something like that already in class where we did, instead of a sum, we did an integral, but we did an integral over x's, x eigenstates, and then we did an integral, that's one basis, and then we did an integral over p's, that's completeness in p, for the p eigenstates, or eigenkets. So those would be that would be an example of two different bases.
Okay.
Did that answer your question, or closer?
Um, I think so. I think actually like I could just look at the homework solutions and see what to do for that problem.
Okay, right. So in any case, whether it's the same list of bases or a different one, the key thing I'm trying to get across here is that when you use completeness twice in a single expression, you have to be careful to label them independently so that this is not getting mixed up with that. Even if they're the same list, you have to run over the labels independently. All right, so let me go on, unless there are other questions. Okay, so let me go on and talk about some more consequences of the postulates of quantum mechanics. So one thing we can do is consider two consecutive measurements. And for variety, I'm going to call my measurements, the operators associated with them, omega and lambda. So I suppose I first measure omega, capital Omega is an operator. And let's say I find a result, which is one of its eigenvalues, which is going to be called little omega. That's one of the list of eigenvalues of capital Omega. And then I measure another observable lambda, and I get the result that's one of its eigenvalues. We'll call it lambda. And when I say consecutive, what I really mean here is that there's no time delay between them. Because if there's a time delay, then the system can evolve according to Schrodinger's equation between the two measurements. And just for simplicity, we don't want to consider that case right now. Okay? And then we can ask the question, after I do two consecutive measurements, what is the final state? Okay, and so we're going to answer this question by applying the postulates of quantum mechanics. And it turns out there are three different possible situations that can arise. So here they are, possibilities. So possibility one happens if omega and lambda happen to commute. So if the commutator of omega and lambda is 0, then they're compatible operators. Okay, that's just saying that they commute. And in that case, we will be left in a state that's an eigenstate of both of them. And so I can label that state as omega, lambda, and then I'm going to put a redundancy label that I'm just going to call J. Okay, so J here is a possible degeneracy label. Okay, and when do you need it? You need it if omega and lambda together are not a CSCO, a complete set of commuting observables. So needed if omega lambda not a CSCO. So they're commuting. They're a commuting set of observables, but they may not be complete. Complete just means that you don't need a degeneracy label. Okay, and so they satisfy the possible states that could be the result of this satisfy omega acting on omega lambda j is little omega, and lambda acting on that state is lambda, omega lambda j. So one thing I want to emphasize is that even though there's a degeneracy label here, the result is not some arbitrary thing. There's a very specific answer to any question of this type, but you have to apply the postulates in order to find out what it is. Okay, so this is not arbitrary. Just because it's degenerate doesn't mean you get to choose any element of the degenerate set. There's a very specific answer for this question in all cases. Okay, so that's if they're compatible or they commute. A second thing that can happen is that they're not compatible. So if they don't commute, let's, for example, say that they're a constant. The commutator is a constant. That's what happens with position and momentum, which is not zero. Okay, or maybe it's not a constant, but maybe it has whatever operator you get from the commutator has no zero eigenvalues. No zero eigenvalues. Okay, then they're called incompatible operators. Okay, and then you will be left after the measurement in a state that's that's an eigenstate of whatever operator you measured last. So we'll be left in a state that's an eigenstate of lambda, because you measured it last, with a possible degeneracy label, again, j. Okay, and this is not an eigenstate of the first thing you measured, which we said was omega. Okay, so here, again, the classic example is position and momentum, but this is true for any operators that don't commute and have no zero eigenvalues. So for example, this is also true of different components of angular momentum, it turns out. So we haven't talked about angular momentum yet, but it's true. Okay, and then there's a third possibility, which is they don't commute, but they do have some zero eigenvalues. So if omega lambda is not zero, but has at least one eigenvalue that's zero. Okay, and then we can't make a statement that's as strong as cases 1 or 2. You just need to calculate it. So in any case, you need to calculate using postulate 5 to get the definitive answer, but there's nothing that we can say without doing that calculation. So then need to calculate applying postulate 5. Okay, questions on that? All right, so let's do another example of applying the postulates of quantum mechanics, this time to a situation where we have continuous eigenvalues. And so what I'm going to do is consider a position wave function, which is going to be defined from minus infinity less than x less than infinity. So we're working in one dimension. And I'm just gonna decree that my wave function, which by the way is equal to the inner product of x, the bra, with psi, the ket for the state that I'm in, is going to be some constant times an exponential, which is going to be a Gaussian. So this is going to be an exponential of minus x minus a squared over 4 sigma squared. A and sigma are going to be constants, and then I'm going to multiply by another exponential, which is going to be I times k times x. Okay, and so C, A, sigma, and k are all going to be constants. Okay, now why am I considering this particular wave function? It turns out this particular wave function has some nice properties that we're going to be using quite a bit in this course. All right, so the first thing I want to do is figure out what C is. Now, in general, C doesn't matter. It's not physically relevant, but it's convenient to choose it in order to make this thing have unit norm. So we are going to choose C to make the ket have unit norm, which means psi is equal to 1. And in position...
Professor?
Yes, go ahead.
I'm so sorry to interrupt, but it seems like we're all having trouble with your voice kind of sounding robot-y and delayed.
Oh, sorry.
No problem.
Not sure what to do about that, except change my internet, but I'm worried that if I change to my other internet provider, it's actually going to be worse, because it usually is.
Oh no, that's unfortunate.
That is unfortunate. Has it always been this way, or is it just today?
I've just noticed it today. It's like especially noticeable today, at least.
I've never heard it. It's just today for me.
I can hear it. I'm not having any issues hearing.
Yeah, I thought it was my internet connection.
Okay. Yeah, I'm not really sure what we can do except just go on and struggle through it.
You guys will try logging out and logging back in. That works for me sometimes, because I'm not having any problems right now.
Yeah, I'm skeptical that my logging back in and out would do anything. So,
Especially because it might ruin the recording. So,
yeah, I think the best thing to do is just struggle on, and yeah, you can go back and listen on YouTube, I guess.
Will it sound better on YouTube because it's coming from your computer?
I think it should, because it's being recorded on my computer and then it's being uploaded.
Okay.
So
But what I'm trying to say is I'm not having problems hearing it. That's what I'm trying to say. I can hear. So, I don't know, Morgan, you want to try logging out, logging back in?
I could, but it seems like a lot of people are having the same problem based on the Discord.
Yeah, and it's not that we can't hear, it's just that it's very broken up. So, I mean, I can definitely learn from this, but it's just kind of a little off.
Yeah. Okay. I think what I'm going to do is just struggle on, and if you really have problems, then I guess I have to refer you to the YouTube, which is unfortunate, but
That's okay. Thank you. And sorry for interrupting.
that's okay. Yeah, thanks for letting me know. All right. So let's see. So we were in the process of trying to choose C to make the norm of this ket be 1. And so what we can do in position space is use completeness. So we're going to integrate over all x. And we are putting in a complete set of states, which are eigenstates of x. That's what I've done there. That should be 1, because I haven't changed anything. And now I use the fact that this is the wave function of x, and this is the complex conjugate of it. Okay, and so this is minus infinity to infinity dx of the complex square of psi. That should be 1. And now just plugging in our wave function, this is c squared minus infinity to infinity dx. And then this exponential doesn't matter because it's a phase. And so when I take the complex square, this just goes to 1. And so I'm just left with that exponential. And so if I plug that in, that's going to be exponential of minus x minus a squared over 2 sigma squared. 2 rather than 4 because I squared the thing. And now this is an integral that you can look up. It's a definite integral. And the result is that it's square root of 2 pi sigma squared under the square root. Okay, and so that should be 1. And so we can get the correct normalization by choosing the constant c to be 1 over 2 pi sigma squared to the 1/4 power. Okay, so now another thing we can ask is, what's the probability of finding the particle in some range? Okay, and let's take a range, just be sort of general, and say the range is b less than x less than c. Okay, so according to the postulate, so quantum mechanics, namely postulate 4. Postulate 4 says the probability for b less than x less than c is an integral, because it's a continuous quantity, of our wave function squared. Okay, this is the probability of being between x and x plus dx. Okay, and so just we plug that into the integral. It's almost the same integral that we had before. It's just that now we're going from b to c rather than minus infinity to infinity. But it's the same integrand otherwise. Okay, and so that's the result of the calculation. Of course, if you had numbers for A, B, and C, and sigma, you could go ahead and plug them in and get a number out. And as a sanity check, the number has to be between 0 and 1. And so that's always a good thing to check. Okay, so another thing we can calculate is the expectation value of x, right? And so according to, this wasn't directly given in the postulates. Remember, this was something we derived as a statistical implication of that. And so the expectation value of x is psi x psi. We don't have to divide by the norms squared psi because we've normalized this to 1. We're going to again use completeness, integrate from minus infinity to infinity dx of psi x x x psi. Okay, and why do we use completeness in x? It's because we can now take advantage of the fact that we know x, the operator acting on x the state, is x the number acting on x the state. Okay, so we've gotten rid of the operator, and so this is now integral minus infinity to infinity dx of x times psi of x squared. So it's the same integral that we used when we did the probability, but it's now got an extra factor of x inside it. Okay, and so we can write this as 1 over the square root of 2 pi sigma squared minus infinity to infinity dx x exponential minus x minus a squared over 2 sigma squared. Okay, and so we have to do this integral. It's a definite integral, so you could always just plug it into some online integral calculator. But just to see how you do it, you would change variables. Okay, and so a good change of variables is to let x minus a be equal to u, and dx equals du.
Professor?
Yes.
Before you scroll down too far, for finding the probability or finding the particle in range b to x to c, in front of that integral, what is that constant supposed to be? Because I'm reading it as 1 over the square root of 2 sigma c sigma squared, and that didn't seem to make sense.
You mean here or somewhere else?
Yes.
Let's see, that should be that. Yeah, that's not very. Let's see, what should that actually equal? C squared. Let's see, there should be a c squared there.
I think it's a pi.
Yeah, I'm just making sure it's actually correct. Let's see, the integral over x. Yeah, so this, let me rewrite it. Okay, so it's 2 pi sigma squared. I got smeared together. Okay. So in any case, when this is also done in the notes, and so you should always believe what's in the notes over what I write in class, because it's possible that I am going to mess it up when I do it in class. Okay. With any other questions on that before I go on? Okay, so we do this change of variables, and so now we can rewrite the expectation value of x as 1 over square root of 2 pi sigma squared. Trying to write it neater this time. Integral from minus infinity to infinity du of u plus a, just plugging in for x. And now there's an exponential of minus u squared over 2 sigma squared. Okay, and now this integral has 2 parts. There's the u part and there's the a part. The u part is just going to give 0. It cancels when you consider the contributions from u and minus u. They're just equal and opposite. And since we're integrating from minus infinity to infinity, for every positive u, there will be a negative u contribution. And so that will just go away. Okay, and then the a part is actually the same integral that we had before. It's just that x has become u. And so this is just going to give a factor of a. Okay, and so the result is going to be a for the integral. Okay, and so if we draw, for example, the wave function squared as a function of x, I guess this goes off to negative infinity, but the Gaussian is peaked at this value a. And so the function itself, when we graph it, looks like some Gaussian. Pretend that's a perfect Gaussian. Okay, so that was the expectation value. We can now do the uncertainty in x. Okay, and so remember we defined that in terms of its square. The square of the uncertainty was equal to the expectation value of the operator squared minus the square of the expectation value of the operator. Okay, we've just worked out that that was a. And so now we need to calculate this quantity, and you can use the same change of variables. So let me just write down what the integral is. once I've changed to the u variables, this is 1 over the square root of 2 pi sigma squared. Integral from minus infinity to infinity du of now u plus a squared, exponential of minus u squared over 2 sigma squared. That's a u. And when I expand out my u plus a squared, I'm going to get a u squared plus 2ua plus a squared. And then just like in the previous, in the expectation value, the thing linear in u vanishes or gives 0 contribution. The a squared is just going to be a squared because the rest of the integral is just going to give 1. Okay, and so this whole thing is equal to a squared plus 1 over the square root of 2 pi sigma squared minus infinity to infinity du u squared times the exponential. Okay, and again, this is not a class on integrals, so I'll just tell you what this is. This is square root of 2 pi times sigma cubed. Okay, and so nicely the square roots of 2 pi cancel, and this just works out to be a squared plus sigma squared. Okay, and so now we can plug in to get that the uncertainty in x is the square root of a squared plus sigma squared for the x squared expectation value minus a squared. And so that just works out to sigma. So I designed the wave function at the beginning so that sigma, the quantity appearing in it, happened to be the uncertainty. Okay, so we're going to do more with this example. But first I want to mention that so far, the exponential of ikx hasn't made any difference. So this factor makes no difference. But it's about to make a difference in what we do next. And so what we're going to do next is to find the momentum wave function of the state. Okay, so how do we do that? Remember the momentum wave function we write as a tilde as a function of momentum. It's still called psi because it's still the same state psi, but it has a different functional form if it's the momentum wave function. It's defined to be the inner product of P, the eigenstate of momentum, with the state psi. And so we can go and use completeness in X to write this as minus infinity to infinity dx px x psi. So I put in a complete set of states and integrated over them all. And the reason for doing that is because now I know the things inside the integral. I know x psi because that was the given wave function, psi of x, that we wrote down before. And px, inner product.
Oh, he's back.
Well, that was weird.
He's back.